Well, welcome everyone. Thank you so much for joining us today for this Kendall Hunt webinar, Transitioning Traditional Earth Science to Earth System Science. Since global problems are highly interdisciplinary, what is the best way to help students understand them? That is what we're going to be going over today. But before we begin, just a couple of housekeeping points. This webinar is being recorded. You'll receive access to that in the coming days. We will be having a question and answer time at the end of the webinar. If you have a question, please feel free to enter it any time within the course of the webinar, and then we'll get to it at the end. So today, presenting with us, we have Kendall Hunt authors Jim Kasting, Lee Kump, and Robert Crane. Welcome, everyone. We're so excited to have you with us today.
Okay, well, thank you, Megan. I'm Jim Kasting, and I'm the first author on our fourth edition of our book, The Earth System. And I'm here with my co-authors, Lee Kump and Rob Crane, to talk to you a little bit about the book, but more generally about our philosophy in teaching earth science or earth system science to students. So let me say just a little bit about myself. To begin with, I'm a planetary scientist / astrobiologist. So my main research interests have been in long-term climate on the Earth, climate evolution on Earth, and also in planetary climates. But I'm also interested in modern global change problems. And I've taught various courses over the years, but one that I've taught for many years here at Penn State is a course called The Earth System. And the book that we'll talk about was written specifically for that course. So our course was a general education course designed to introduce students to the problems of global environmental problems. But the book can be used on a variety of levels. We know it's used for majors at some universities, and it's actually been used as an introductory book for grad student astrobiologists at other places. So let me say what the general philosophy of our course and our book is that we're interested in the earth science in general, but we're also interested in global environmental problems. And there's three that we focus on in our book: global warming, ozone depletion, and loss of biodiversity. And what we try to do is teach earth science through the lens of these environmental problems. And as I mentioned, we're trying to here educate general education students, non-science majors mostly. But these are problems that we think students should be knowledgeable about in many different fields. So there are a number of good earth science books available out there. And one of the most successful is a book by Tarbuck and Lutyens called Earth Science. It's in its 15th edition, so it's been around for quite a while. And when we started teaching our course, we looked at books like this one and others, and they're very good for what they do. So Tarbuck and Lutyens has 7 sections. You can see them listed here, ranging from earth materials, forces within, those are plate tectonics, earthquakes, etc. All the subjects that are traditionally studied in earth science and geoscience departments. So that's good, but what we were interested in teaching in our course, The Earth System, was global change. And if you look at the outline here, I've listed in red how many papers are explicit, or how many pages are explicitly devoted to global change problems in this textbook. It's about 60 pages total out of 800. So there's a lot of material that's very good material, but not relevant to what we wanted to teach to our students. So what we try to focus on in our course and on the book is what we call Earth System Science. as I said, we're in the fourth edition of our book, The Earth System, which we wrote for this course. And that's because when we all started teaching it many years ago, we couldn't find a text that really covered the subjects that we want to cover. So our book has 4 sections. There's an introductory section of about 30 pages, which is explicitly about global change, especially modern global change, but a few past global change problems. Then we switch into a discussion of the components of the Earth system. This is more closer to a traditional Earth science text because it covers different aspects of the Earth system. But it's also different because we focus on things like the greenhouse effect and climate modeling that are important for the global warming problem. We have a big emphasis on the carbon cycle because that's what controls CO2 and also methane. And then we're interested in biodiversity as well. Then there's a long section on the history of the Earth and of life, and that's included partly because we were interested in those subjects ourselves, but also because, I think we all feel that it's really impossible to understand the modern and global environmental issues if one doesn't have a sense of how the Earth has evolved over time. And then finally, the last section of the book is on the effect of humans on the Earth system, which is when I teach the course, that's really what I'm trying to get across to the students. And that's, so we talk explicitly about climate change, ozone depletion, and loss of biodiversity. And so that's a major theme of what we talk about in the course. Okay, so that's enough for me for right now. Let me introduce my first co-author here, Lee Kump. Lee was the first author of the first 3 editions of the book. He's now our dean of the College of Earth and Mineral Sciences here at Penn State. So I took over as first author, but Lee is the one who thought about this concept at first. So Lee, it's all yours.
Well, thanks very much, Jim, and thank you all for joining us here today. Yeah, he did mention that I've gone over to the dark side of academic administration, but still do keep my hands into a little bit of teaching, and very interested in continuing this process of transitioning education from Earth science to Earth system science. I've always been grounded in interdisciplinary approaches. My undergraduate work was in geosciences, but my PhD is in marine science. I was the second hire into a new concept and a new research center at Penn State, the Earth System Science Center. Actually, the first hire into that center was Rob Crane, who's our third co-author here, and he'll be speaking in just a minute. And so I've really spent my entire career doing Earth system science, which for me is sort of taking a top-down approach to understand how the Earth functions as a system and how it's evolved through time. Jim mentioned the course we've developed, and I say we because it really was a group effort that drew on our respective areas of expertise and background. And I think, one of the greatest challenges for us, for me, was to decide how to distill down the essential knowledge that a student needs to understand how the Earth system functions, evolves, and might be responding to human activity, because we obviously didn't have time to go through all the background of biology, physics, chemistry, environmental science, Earth science. That'd be a tremendous task. So we did have to do this distillation process, and frankly, it took several years and some embarrassment in the classroom when I would launch into some topic and then realize the students didn't have the background for it, have to do some backpedaling. But I think over the years, we've come to understand what that essential knowledge is in the multiple disciplines that contribute to Earth system science. And I think our book reflects that. So I think, for you if you're thinking about adopting it, or if you have adopted it, there's that experience of, there's a really great learning opportunity here for you to expand your understanding of how the Earth system operates. I certainly went through that myself, and in doing that, come to appreciate what these essential aspects are. And it really comes from that top-down approach, things like global scale, energy, and mass balance. And I also have benefited from my early and continuing work with the originator of the Gaia hypothesis, James Lovelock. Some of you may have heard of him. He, with Lynn Margulis, proposed in the 1970s that we should think of Earth as a living organism, as a system comprising the biota and the non-living components that operate together to create a sustainable and habitable planet, and have been able to sustain that over the eons. So we actually incorporate Gaia concepts into the book, especially around the development of understanding around feedback loops, around stable and unstable equilibrium states, resilience of the Earth system, recycling, as in the carbon cycle. And we also emphasize that life is a truly globally relevant force shaping the Earth system. The most recent manifestation of that is human activity, but a concept that developed over the course of my career is one from a sense that life just has to respond to the physical world as it evolves, to one in which there's coevolution of life and environment. Jim, if you go to the next slide. One thing that Lovelock did to try to convey this was to think of a world in which the only life form are daisies, and only one environmental variable matters to them, and that's temperature. And in Daisy World, the daisies are part of this system, global system, that actually regulates the temperature to stay within the tolerance limits of the daisies. And this doesn't involve any foresight or planning on the part of the daisies. It simply arises as an emergent feature of their interactions, that recognition that as the gray daisies or as the white daisies spread across a gray soil, the planet becomes more reflective, and that cools the planet. Similarly, daisies will have minimum, optimum, and maximum temperatures for growth. If we go to the next slide, Jim. And so this provides a mechanism. I won't go through the details of this, but just a sense of some of the figures that are in the book that highlight that there are equilibrium states here, stable equilibrium states, these valleys here in the lower left. If we're looking at surface temperature as a function of a sense of stability, and unstable equilibrium states, where the slightest perturbation might send the system into a very different state. This helps us convey to students this concept of tipping points, that while the Earth system may be resilient, as long as you're in the bottom of that well, that if you move out of those zones of stability, you can end up in a very different state. And then the slide on the right just shows how the temperature on Daisy World is stabilized over the course of its planet's history for much longer within the realm of habitability for the daisies than it would be in the lifeless case. So we developed that understanding of Earth, of system science, through the application of Daisy World, and then we apply that through the rest of the book to understand, the stability and resilience, but also sensitivity of the Earth system to disturbance. And of course, this is leading up to, as Jim mentioned, this focus on modern global change. And if you think of the Earth as a living organism, then global warming, for example, might be thought of as an illness. for which we are seeking cures. As planetary physicians, in this case, we're thinking about not just scientists and educators like yourself, but the people of the world. We first want to understand the history of the patient. And so we, in the book, spend considerable amount of time looking at Earth history, looking at past climates and other environmental changes, and how the Earth responded to this, why we're still here after 3.5 billion years of biological habitation of the planet, suggesting a habitable planet was facilitated through that, in spite of lots of disturbances. We focus, for example, on the faint young sun problem. The likelihood that our sun was 75% as bright early in its history, and it's warmed up through time, increase in the insulation the planet receives. How did the planet keep from freezing over in the Precambrian before 550 million years ago? Or what kept it from overheating since then? And if we develop this understanding among our students, we instill in them that sense of resilience provided by negative feedback loops. Next slide, Jim. We also, of course, are interested in disturbances and abrupt events. Certainly fossil fuel burning and anthropogenic climate change, landscape modification. These are abrupt events from the perspective of the history of the planet. And so we include, for example, discussions around mass extinctions caused by asteroid impacts and massive volcanic eruptions. And this is just the history of those extinction events over the last 550 million years, that punctuated nature of it. What drove those extinctions? How did the climate system respond? How did other aspects of the environment respond? How did the biota respond and ultimately recover? And those massive perturbations demonstrate both the sensitivity to disruption, but also the resilience over longer time scales. Okay, I'm going to turn this over to Rob Crane now. He's an emeritus professor of geography and our emeritus associate vice provost for global programs at Penn State. So Rob, over to you.
Okay, thanks, Lee, and hello, everyone. As you can see from this short bio here, my background's a little different to Lee and Jim. All my degrees are in geography, and my early research was on microwave remote sensing of sea ice and ice climate interactions. And, if you're looking at sea ice at the distribution or thickness, the extent of sea ice, that's a function of both thermodynamic and dynamic processes, and it involves interactions with both the atmosphere and the ocean. So that's inherently a multidisciplinary problem, and it requires a systems approach. And then later, I did a lot of work on downscaling climate models for regional climate data, looking at climate change projects mainly in Africa. And again, that was with multidisciplinary teams of sort of physical scientists, ecologists, social scientists, educators. So I've always had a very systems and multidisciplinary perspective on the work that I do. When I first got to Penn State, I did a lot of teaching in climatology and remote sensing. But I also taught some introductory physical geography classes. And back then, the texts were all very similar and the classes were all very similar, right? So the text would have, and the classes would be divided into 3 sections. There'd be a section on geomorphology that might include a bit of plate tectonics. There'd be a section on an introduction to biogeography, and then one on an introduction to climatology. And these texts all had 2 major sort of weaknesses or flaws in them. One is that none of them looked at the links between those 3 different parts of the Earth system. They were all treated in isolation, which means you only ever got part of the story. And the other is that apart from one text by somebody called Jeff Dozier, who incidentally was another geographer who worked on the cryosphere, but apart from his, all the texts were highly descriptive, right? They would talk about the world in terms of existing patterns with no real attempt to explain how those distributions got that way. So when we approached our text, as we started to develop the Earth Systems class, we took entirely the opposite approach. So Jim, if you go to the next slide. So if you're, looking at the global energy balance, it's actually very simple. It's easy to talk about the planetary distribution of radiation. You can easily calculate the radiating temperature of the Earth and calculate the magnitude of the greenhouse effect. And we do that in the text, and that actually forms the basis of a lot of discussion that keeps reoccurring all the way through the text. But when you're looking at the detailed mechanisms by which the atmosphere and ocean, why they circulate, how those circulation patterns are formed, how that involves the transport of energy and mass around the system, what controls precipitation, all of this is a lot more complex, right? And it's required, and all of it sort of interacts with each other. So approaching that, you end up talking much more about the physical processes. So, Jim, if you go down the next slide there, in our text, we might show a map of the distribution of temperature, global temperature. But the discussion in the text doesn't just talk about that temperature. You get to that map after a long discussion about the energy balance, latitudinal energy distributions, rotation of the Earth, convection, how all of these processes, these thermodynamic and dynamic processes, lead to a particular pattern of atmospheric circulation and how that then affects rainfall and temperature. And if we go to the next slide, that sort of gets reinforced when we show how atmospheric circulation drives the surface circulation of the ocean, how that gives you warm and cold currents in different parts of the ocean off different coastlines, how that results in different climates, the same latitude, but different climates on the west and east side of continents. So all of that comes from this sort of top-down systems approach, right? It allows you to make those connections. What's interesting, though, from my perspective at least, is that as you talk about processes this way, and as you have to talk a bit about the ocean, a bit about the atmosphere, if you have to talk about Coriolis and so on, then instead of sort of lecturing, it becomes much more like storytelling, right? You're bringing a little bit of this and a little bit of that, and you're building a bigger picture as you go along. And there's sort of certain advantages to that. And one of the things that happens when I teach this course, at least, is that, you have something up here that's showing, you might be explaining the monsoon, Southeast Asian monsoon, right? To me, when I'm talking about the monsoon, I immediately then start talking about the Arab influence all along the east coast of Africa, right? Why that happens, and why Swahili is the common language along that coastline. And that is all a result, a function of that monsoon circulation. You explain why the doldrums are there, and that leads me to Coleridge and the rhyme of the ancient mariner. Maybe you're talking about volcanism and effect of volcanoes on climate. So you're mention Tambora, the eruption in 1815, the following year without a summer. And that leads maybe to mentioning Mary Shelley and Frankenstein. Although, as far as I know, there's absolutely no evidence to show that her writing was affected by the weather that year at all. But, this sort of diversion as you go, most students don't like it for most classes. But in this class, it sort of helps a little bit because, as Jim said, this is a class developed for non-science majors. So, it gives them something else they can relate to. But another advantage of this sort of approach, this top-down approach, this systems approach to things, is it gives you a very different way of asking questions in the classroom and a different approach to exams. So, for example, if you ask students, get in a group and talk about what would happen to the latitudinal energy distribution if the Earth was a cube rather than a sphere? How would climates change in the US if the Earth rotated in the opposite direction? If students can sort of work through that, maybe draw some systems diagrams to show some of this, and they can explain what would happen, then you know they really have understood the concepts and the principles involved. And that leads to a further advantage in that, despite the fact that it's a very complex system, there's actually a very small number of basic underlying principles that and processes that students have to learn about. And if they can get that understood, then they can build their own answers from there, right? So instead of looking at a map of climate distributions and saying, what is a Mediterranean climate and where is it on the Earth? You can point to a part of the Earth and never having mentioned Mediterranean climates in the classroom, you can say, what would the climate be like here? And if they know those basic principles, they can work out that that would be what we would label the Mediterranean climate. So another advantage here is that aside from the fact that you can recreate or the knowledge, you don't have to memorize everything. It also gives you a very different way, or at least a possible way of talking about things that might not be so obvious, that are counterintuitive. For example, having gone through this process, it's then very easy to talk to students about why in a warming climate, why in the place we live, in the mid-Atlantic region, why it would be possible to get colder and snowier winters when everything is supposedly warming up. And so that leads us back to the third part of the text, which is back to Jim. Jim?
Jim, you're muted.
Sorry, I'll try to be brief, but I want to talk a little bit about the three problems that we started out with I mentioned at the beginning here: global warming, ozone depletion, and loss of biodiversity. So let me start out with global warming, which is my own favorite topic to read up on and to try to do something about. Figure 2 in our book is the Keeling curve. So that's shown here. This is the record of CO2 concentrations measured on the flanks of Mauna Loa volcano out in Hawaii. Measurements were begun in 1958 by Charles David Keeling of the Scripps Institution of Oceanography. So that's why it's called the Keeling curve. And of course, you can't miss the long-term trend. CO2 was about 315 parts per million when Keeling started measuring it in 1958. It's gone up to 420 parts per million today. If you look at ice cores, which I'll mention briefly in a moment, we get a record that goes back much farther than that. And we know that prior to man's influence, the so-called pre-industrial CO2 concentration was about 280 parts per million. So CO2 has gone up by about 50% as a result of human activities. And I should say these measurements are very secure. Nobody argues about the measurements, and almost everybody agrees that the CO2 increase is caused by humans. There's also an annual cycle here of about 6 parts per million, which you can see, and that's caused by the so-called breathing of northern hemisphere forests. So Hawaii's in the northern hemisphere, and forests take in CO2 during the summer, so CO2 is low in the fall, and they respire during the winter, so CO2 goes up then. And so we talk about that in chapter 1 and in more detail in the carbon cycle chapter. Now, the related graph to this, which is just after that in Chapter 1, is global average temperatures from 1850 up to 2021. This is from the figure in the book is a couple years old. I'll show you a modern one in a second. But what you see here is that, first of all, you start in 1850 because that's when Fahrenheit invented the thermometer. So before that, we just have proxies for temperature. You can see that there are these gray bars here are error bars on the curve. and they're very large up until about 1960 or 1970. And that's because the measurements were made from ground-based weather stations and from ocean-going ships. And so the spatial coverage was poor, as was the temporal coverage. But for the last 50 years, beginning in about 1970, we've had a record from satellites. So that begins right here. You can see that the error bars are much smaller, and that, of course, the temperature has been going up quite noticeably over that time by about 1.2 degrees Celsius by the time this curve ends. Now, notice also that there's a fluctuation here, very distinct sort of bimodal fluctuation. That's the pattern of El Niños, caused by El Niños and La Niñas. And that's seen more explicitly in this updated slide, which is not in the book, but if you were teaching the course, you would want to show this. So if you've been following the papers at all for the last year, 2023 was really hot in many areas of the world. So here it is. This includes 2022 and 2023. And 2023, the global temperature anomaly, that is the increase in temperature since the 1850 to 1900 mean, is almost 1.5 degrees Celsius. And just as a side note, that's about the upper limit on warming that was specified in the Paris Climate Accords back in 2015. So we're already at the point of exceeding the amount of warming that was agreed on as an upper limit at that time. Notice that these red dots are El Nino years. That's an coupled ocean atmosphere oscillation that we discuss in some detail in the book, because you can see it has a big effect on the temperature record. Temperatures are higher during El Nino years. They're cooler when in La Nina years, which is the opposite of El Nino. And these black squares are so-called neutral years. 2023 is listed as a black dot here, which is kind of surprising. We're actually in a big El Nino right now, but it didn't start until May, so almost halfway through the year. So temperatures could get even warmer next year if the El Nino continues. Now, the effects of warming, that was global average surface temperatures. The effects are seen even more strongly in the Arctic. So these are 3 pictures of the Arctic sea ice minimum at the end of Northern Hemisphere summer, late September, when the sea ice is at a minimum. And what you see here is that in 1979, the sea ice at the minimum extent went down all the way to the coast of Siberia. And you can see that the Canadian Arctic was entirely, the passages between the islands were covered in ice. So that for many years, the traders had looked for the Northwest Passage, which was never open until fairly recently. So now if you go to 2012, you can see a marked difference here. There's lots of open water between the Arctic ice pack and Siberia, and there are channels through the Canadian islands through which ships can now get. So the Northwest Passage from Europe to Asia is now open at least part of the year. In 2021 is roughly the same as 2012. There are fluctuations that go back and forth during the years, but we expect that Arctic sea ice is going to continue to diminish, and we may have an ice-free Arctic Ocean within the next few decades. Let me switch briefly to ozone depletion here. I'll just show you one chart here. Most of you have probably heard about the ozone hole that's shown in this graph at the bottom, which shows ozone column depth, the total amount of ozone between you and the top of the atmosphere in Dobson units. And this is these are data going back to 1960. They're ground-based measurements from Antarctica, from Halley Bay in Antarctica. You can see that up until about 1980 or so, ozone was about 300 Dobson units. Then it started falling rather precipitously. That's the ozone hole. So these are measurements actually during the month of October. That's when the hole appears. The hole was discovered from ground-based measurements at Halley Bay, which was surprising because these green dots are TOMS. That's from the Total Ozone Mapping Spectrometer. That's an orbiting satellite, which was already up by about 1978 or 1979. But it was the researchers at Halley Bay that published the first report on the ozone hole, and that's because the satellite people were throwing out data that they thought was bad because it didn't have enough ozone in it. So that's a story that we tell in chapter 1, which goes to show that the limits of high technology sometimes. Now, Antarctica plays a big role in our book because it also is very relevant to climate. I'll just mention a couple of things here. Thwaites Glacier is sometimes called the Doomsday Glacier because that is sort of based on it's supported by contact with an offshore island, and if you get a little bit of warming of ocean water, that could slide, and we could get a meter or two of sea level rise just from that one glacier. There's also, as I mentioned earlier, a historical record from ice cores in Antarctica. There was an initial ice core at Vostok, dug by a collaboration of Russians and French, and then the more recent one from Dome C. So these are both near the center of the Antarctic ice sheet, and these give you records of temperature through isotopes, but also CO2 and methane and N2O going back almost 1 million years now. So that has been very useful in putting the modern climate change into context. Then last thing I'll talk about very briefly is biodiversity. I'm not that knowledgeable about biodiversity myself, but some of the people that teach our course, like Sarah Ivory here at Penn State, spend a lot of time on this subject. This is a diagram that's showing biodiversity hotspots. And we read frequently about deforestation in the tropics, which is causing loss of biodiversity. But actually, deforestation and habitat loss has been causing loss of biodiversity across the globe, including in Europe and in parts of the United States. So it's a big problem. In fact, when I teach the course, I ask at the very outset of the Earth System course, I ask the students to write an essay saying which modern environmental problem between these three they consider to be the most serious: global warming, ozone depletion, or loss of biodiversity. And many of them reply biodiversity loss, and I tend to agree with that because biodiversity loss is, for one thing, it takes millions or tens of millions of years to recover from, and for another, you never do recover to the same state that you started in. So this was a good thing for us at the KT mass extinction, which Lee sort of referred to it in passing, but that's the one 65 million years ago where the dinosaurs got wiped out and they were replaced by mammals, including us. But we're in the midst of a 6th mass extinction right now, one caused by humans, and that could have very serious and long-term consequences. So with that, I'll quit talking, and we'd like to open this up for questions and see if there are any. Thank you.
Okay, we do have one question here. Let's see. Hans, I'm going to allow you to speak and ask your question, okay? Give him a moment here. Okay. Well, in the meantime, one question that we do have is, given the scope of your title, what are some sort of successful trajectories for going through the book?
Jim, do you want to start with that? And then we can, I think that we have three trajectories here, probably among the three of us, and other trajectories have been taken at Penn State and at other institutions. So, Jim.
Yeah, so we teach the Earth System course quite differently here at Penn State, depending on the instructor's background. I mentioned Sarah Ivory. She's a young paleobiologist, so I co-taught the course once with her when she was learning to teach it, and she's very interested in biodiversity, which is great, and she knows much more about that than I do, so she emphasizes that. I emphasize climate change. Lee, I think you emphasize Earth history a lot, and I know Rob emphasizes modern day climate and also sea ice and all these things that the climatologists really care about. I think I also mentioned that at some universities, our texts can be used at various levels, and I know at RPI, Rensselaer, they actually use it in an introductory course for astrobiology graduate students because they want these students to have a grasp of the whole Earth system. And their students come from a variety of backgrounds and don't always have Earth science. So a text like ours is just perfect for them.
Yeah, I think, one common thing is, I think, is that folks, everyone uses the first several chapters that are focused on how the modern Earth system functions as a system, brings in the components, the geological components, the climatology and weather, and and the biological components. And so I think that's a fairly common starting point. And then, as Jim mentioned, depending on your predilection or strength, you might focus, like in my case, as Jim pointed out, because I love Earth history and all the great things that have happened in the past. I mean, I always tell my students that everything that we can imagine we might do to the planet has been done by itself or through external forces like asteroid impacts in the past. So there are a lot of, the past is the key to the present and the future. So I tend to focus on that. I think everyone also will bring in especially the climate change themes. And so you can go through this with a real focus on climate change, for example, and you do the systems chapter, Daisy World, you do the energy balance, you talk about the physical climate system, biological impacts on that, but you might focus in your Earth history part on just the climate change related aspects of it, and maybe not touch on the biodiversity through time, for example, mass extinctions, or you may not focus on ozone chemistry and the ozone hole. So so I think, well, that's been my experience. Rob, do you have a different one?
No, really, it's pretty much the same. And I think everybody does start with those first few chapters and, a description of the system. I tend to focus a lot on the system, Daisy World and systems and feedbacks, because I then use that all the way through the semester. I think a little while ago, Jim said that the biology was his weakest point, or the ecology. My weakest point is chemistry. So I have to admit those chapters with lots of chemical equations in, I skip through those fairly quickly. And I tend to end up doing a lot more on climate. In terms of history, I like the Faint Young Sun one because that really lets you talk about feedback processes and what's affecting the climate system over time. And then I spend a lot of time on future climates and biodiversity. Maybe I talk about the ozone hole, but maybe a little less than some others might. I think the point is there's a lot of different ways to work through this book. And
I think one thing we have, sorry, go ahead, Rob.
So one thing we've had to do, because quite a few semesters we'd have multiple sections going with different instructors, is we'd have to tell students that unlike other classes, They can't bounce from one section to another because they got up late on the day that they were meant to be in my class, because what would be happening in the other classroom would be completely different.
And I think for some of you, I mean, for us, this was a general education natural science course. It wasn't meant to be a prerequisite for anything else. And that gives the instructor ultimate flexibility in terms of what to cover. Some of you may have explicit requirements around geology, for example, and we have chapters that go into the basics of geology. In that case, you might want to supplement it. You might want to supplement it with some of your labs that you've developed, in rocks and mineral labs, for example. So there are ways to use the book as a backbone, and then to bring in some of, even your existing content to supplement what the book is providing, to provide those mandatory topics that you might have, or to draw upon your own expertise and interest as well.
Yeah, excellent. Says, we have a question here. Apologize if this question was already answered, but are you using this course as a different version of Earth Science, or as a course that would follow sequentially within Earth Science as a prerequisite?
This is fully standalone. Penn State has requirements for all students to get general education course requirements. So the main place that this book is used in is in our course Earth 2. It doesn't have prerequisites, nor does it actually does serve as a prerequisite for some more advanced courses in the geosciences as an alternative to the introductory geoscience course. But we the earth science majors in our college, and in particular the geoscience BS majors, would typically take the more traditional introductory to geoscience course here at Penn State. Anybody want to add to that comment?
Well, I mentioned astrobiology. Astrobiology is the search for life elsewhere, but also the study of the origin and evolution of life on Earth. And our book, unlike most Earth science books, most of them are focused on the Phanerozoic for the Earth history part, the last 540 million years where we have a good fossil record. But astrobiologists are interested in the whole 4.5 billion year time span. Lee, you mentioned the faint young sun problem. That's something I've worked on personally for many years. But there's other things like the rise of oxygen. That to me is one of the most fascinating parts of Earth history. I mean, I talked about ozone, but you wouldn't have any ozone if you didn't have oxygen, and we wouldn't be around because we wouldn't have anything to breathe. So, there is a chapter on the rise of oxygen, and as you know, Lee, we're still debating parts of that. So it's
well, right. And I was just thinking, my mentor James Lovelock, the Gaia hypothesis person, called that the greatest pollution event in Earth history, because you had a world of organisms thriving at the time that couldn't tolerate oxygen, and suddenly cyanobacteria invented how to produce it. And then at some point later on, that's the debate, oxygen became established in the atmosphere, and those oxygen hating organisms were driven into the mud. And
they didn't go extinct, though. Biologists tell me that they all just retreated to environments that were more favorable to them.
Excellent. And then something else that I'm curious about is, because your material is so comprehensive, how do you make sure to have meaningful conversations in the classroom when there is so much that you could be having a conversation about?
You have to limit yourself to, you can't do all 20 chapters in a 1 semester course. You might be able to get through them in a 2 semester course, but for a single semester like we do, you have to pick and choose. As Lee and Rob have said, most people do the first 7 or 8 chapters, and then they pick and choose after that. So you can't really rush any course more than a certain amount without losing the students, and we're well aware of that.
I think also, as I mentioned earlier, you know, faced with teaching the Earth system and thinking about the biological and physical components and thinking about what you traditionally teach, we are combining what would typically be in introductory and maybe advanced biology, ecology, some aspects of chemistry, oceanography, meteorology, things that for which there are introductory textbooks, very, mostly very descriptive. And as I mentioned, we had to distill down that essential knowledge. And, we've been doing this for over 20 years. And so through several editions of the book, and thanks to Kendall Hunt for bringing us up to date with this new edition. But what we hope to provide to you is that essence of what students need to understand, to have those meaningful discussions around the comprehensive view of the modern challenges to the Earth system around climate change, global pollution in general, biodiversity loss. And so I think that makes it doable. And as we've been discussing, you don't have to do everything to be able to have those. You can track a trajectory through the book. And by the way, Jim and Rob and I still here, and always happy to answer your questions. What would you recommend as a trajectory through the book for my class that has these learning objectives? So feel free to reach out to us at any time.
Yeah, another point that I think Lee made earlier too is that for us, this is a general education class. So there are very few there are very few classes that follow this that require us to have talked about something specific. And so that, for us at least, gives us a bit more flexibility too, right? As soon as you lose that idea that I have to teach everything that's here by the end of the semester, then you can afford to spend a little longer on one thing, a little less time on something else, miss something else completely if you need to, and keep the attention of the students going by focusing on the things they're interested in. But of course, if this is a prerequisite for something else, then that's not quite as easy.
And there's a question here about associated labs. And, we have always taught this as a lecture discussion breakout, active learning, but in large lecture halls. And at other institutions, though, folks have paired this with laboratories. For some of them, there are mandatory laboratories that they have, and I mentioned some of that if you have a physical geology course that has mandatory labs, you can work those in. Others have utilized online resources to bring in more of a like a modeling perspective, so students can have a chance to play around with your system. And for those individuals, we've had some resources available at Penn State, but Carleton College and the SERC website, SERC website, is a great resource for people who want to bring that in. So no, we don't have a lab manual associated with the book. People have developed labs for that run in conjunction with courses that use our book. Be happy to try to put you in touch with people, so you don't have to reinvent the wheel there once again.
There are homework problems, and there's a homework manual that gives the answers. So
yeah, and we've used those critical thinking questions as ways to engage students in the classroom, and break out into groups if you have that ability in your class. So there are the questions that we ask are fairly interesting, and not just necessarily calculations that they turn as homework, but can be the seed for a broader discussion.
Absolutely. I think we have time for one more question today. John would like to know, the topics you cover almost certainly lead to questions/debate regarding pressure for economic growth versus sustainability, which themselves lead to ethical, equity, and political issues. Are the latter addressed in the book?
There's a whole new chapter on policy solutions for global warming, and it actually has some of the economics in there. If you read that, you'll find out that the economics are really not as unfavorable, for fighting climate change, are not as unfavorable as people think. If you treat future generations on the same basis as we treat ourselves, then it makes good economic sense to deal with the climate problem. So that's part of my own motivation for working hard on this book, is to get that point across.
Excellent. Well, that concludes our time today. Thank you everyone so much for attending. Just as a reminder, we will be sending the recording out in the coming days, and we will also provide the author's contact info for you in case you have any further questions. Thanks again for joining us. Jim, Rob, Lee, thank you so much for presenting with us today. It was truly a pleasure.
Yeah, it was our pleasure. Thank you all for joining.
Right.